introduce to you Coluna, which is an open source branch cut and price framework. So in my talk, first I will briefly tell what is Coluna.jl. Then, since it's used to solve decomposed problems, I'll tell a bit about the decomposition approaches, and then how to use Coluna to decompose and solve your model. So this is how Coluna is placed in the JuMP environment. So the user is able to use it through JuMP and MATLAB interface. And for that, he also needs block decomposition.jl, which is a package that is also developed by us. And what it does, it's implement a few macros and functions that extends some JuMP functionalities in order to allow the user to define his decomposition using the variables and constraint indices of his JuMP model. And Coluna is there to take all this information to solve the substructures defined by the user using block decomposition. So Coluna is fully open source, developed, written fully in Julia. We are using the latest versions of the packages, and the uses for it would be to solve Dancy-Wolf and Bender's decomposition. There's also in the future applications for robust and stochastic optimization. And so the first release was in January this year, but what I'm presenting you is not corresponding to this release because we are redesigning block decomposition and Julia. We are updating everything, and also we have the support of MOS. So a bit about decomposition approaches. Here I'll talk mainly about Dancy-Wolf and Bender's, and you can see this as one being the dual of the other, in the sense that in the Dancy-Wolf, you decompose on the rows, so we have many resources. We have multiple resources, and these are linked by these blue rows, where the linking constraints. And whereas in the Bender's decomposition, you have multiple decision levels, and these are all linked by these blue rows. So once you fix your blue rows, all your subproblems, they can be solved independently. The same for Dancy-Wolf. So an example of a problem that can be decomposed using Dancy-Wolf is the cutting stock problem. So in this problem, you have some stock material, one-dimensional stock material with fixed width, and one must define cutting patterns in this stock material in order to cover demands of items. So you have to cut these big pieces into small pieces in order to satisfy these demands. So here are linking constraints that basically says that among all the cutting patterns that you define, you must cover the demand. And these are your subproblem constraints that basically just say that for every cutting pattern that you define, it must satisfy the knapsack constraints or the width of your stock material. So now, how do you reformulate a problem? In the simplest case, imagine you have your F problem, where it's composed by these two parts, the blue part and the green part here. And the blue part is making your life hard, and the green one is what we call the subproblem. And imagine this is relatively easy to solve compared to the original problem, the F problem. By relatively easy, I mean that in theory you can enumerate all your integer feasible points to the green problem. And let's say you can do that and call this integer, this set of points x. So with this set of points, you can define the convex hull of x. So the best possible formulation for x, you can define by saying that it is a linear combination of the integer feasible points. And now you have your lambda variable for each of these points, and this just tells how much you use of each of those points. Now, if you think lambda as your variable for your original problem, you can do this reformulation. Now your F problem is described only with lambda variables, and now your blue constraints, now they just use the lambda variables to satisfy the demand, and your subproblem constraints basically just say that you have to use one solution for the problem. Now coming back to the cutting stock example, the reformulation for this problem would be something like this. So we minimize the number of cutting patterns that you use, subject to covering the demand. Now you may ask, so if you're enumerating all your integer feasible points to an integer program, this may lead to many points. and this is true, but we actually don't generate these points a priori. So this is now I'm going to talk about how to solve the problem once it's decomposed, and we actually don't just generate the points that are interesting for us. So if you take a branching bound, and the difference here for a normal branching bound is that when you're going to solve a node, instead of just solving an LP, you iterate on solving the LP of the master problem and generating this new columns, these new variables, the lambda variables that are actually interesting for you. So you generate only those that will decrease the objective function of the LP of your master. So imagine we are minimizing. And you use that typically with an oracle that produces the solutions for your subproblems. So I don't know if you can see, can you see this? Okay, so this is a log of Coluna. So basically here we are solving a node, and you see here that, so this is for an instance of the generalized assignment problem. So with 100 items, so it's not that small, it's already quite big. And you see that the time to solve the master and subproblems, they're very small. So this is kind of the divide and conquer effect. So you solve many times small structures, but these are typically much faster than solving the big problem at once. And so here you see the MLP bound and the dual bound. So these are the bounds, the primary and dual bounds for the LP on your node. So these bounds, they will converge by the end of the solution process of a node. So why would you use decomposition approaches? First, you can exploit the structure of a problem, as I showed, and these reformulations can be done through generic schemes like Benders and Danzig-Wolf. The size, which a priori seems like a problem, it's actually not the hardest problem, because you just generate dynamically these entities as you need them. And so these kind of algorithms are not so simple to implement. So a PhD student are doing his research, they will spend a whole PhD implementing a branching price. So we're here to provide a generic implementation for this kind of special branching model. Now, a bit on Coluna, how you use that and to decompose and solve your model. First, I'll tell you the general idea of the, let's say, the interface for the user, and then I'll give you a few examples. So the general idea is basically you want to reproduce this kind of structure, right? So this is the typical structure of your problem, and you want to tell the solver, in this case Coluna, okay, this is my prior problem, and we have these three subproblems that each of these subproblems have these and these variables and constraints, okay? So we do that so the user defines his JuMP model for his problem as if he would feed it to Simplex, but with some few extra informations that are given through block decomposition. So it basically tells, using the variables and constraint indices, which is going to be his decomposition. And you use that, and he does that through the axis macro, which is defined in block decomposition. And then once he defined his decomposition, he calls the Danzig-Wolf decomposition macro, and this will take all this information and put it in the right places. So a few examples. First, the generalized assignment problem. This is a problem where you have a set of items and a set of machines, and you want to minimize the cost of assignment of items to machines. So the cost here depends on items and machines, and also the weight of each item depends on the machine that is assigned to. So we have your master constraints here, the blue ones, that says that you have to cover all items, and you have your subproblem constraints that for each machine you have one subproblem. So we have, in this case, 3 machines, 3 subproblems. You have to respect the capacity of the machines. So this is what basically happens. This is your structure. So you have your 3 machines here, your master constraints linking everything. And what block decomposition does is that when you define your decomposition, it will generate this tree, which just links everything, all the entities together. So you have your original model, you have your decomposition, let's say deck, and you have your master and subproblems, one for each machine, linked together. And this is the information that Coluna uses to know which structures to solve at each time. So the code that generates this, I hope you can see, actually from here, from the model definition to the objective function definition, this basically doesn't change for standard JuMP model that you would feed it to Cplex or Ruby or whatever. The only thing that changes is that you define this axis here, machines. So here I'm defining machine axis that has 3 indices. So it means I have my decomposition will be done in machines, and I have 3 machines. Now all my constraints and all my variables, they will be indexed in machines. And this is how we know where to put each variable and each constraint. So if you see here, we have X, JM for M in machines. And then once we have all this, we just call the decomposition, we give it a name, we say which axis I'm doing the decomposition on, and that's it. Now the next example is the cutting stock example. And for the cutting stock, you may have as I said before, you must define cutting patterns, and you don't know how many cutting patterns you will need to cover everything. It's not like in the gap. In the gap, you know how many machines you have. Here, you don't know how many cutting patterns you will actually need. So you may just say, okay, I need at most 100. I'll never use more than 100. So I define 100 subproblems, and you can do that, and Coluna will solve 100 times the same subproblem, because actually, if we see at the cutting stock problem, all the subproblems are the same because they have all the same width, and the weight of each item does not depend on the machine, in this case on the pattern that you're defining. Or you can say that, okay, I may use at most 100 solutions, 100 patterns, but they are actually the same. So you give this information to Coluna, and Coluna actually will define only one subproblem and use at most 100 columns of that. And this is the decomposition tree that we define. We have here only one subproblem, and you have a lower and upper bound of how many columns you can use of 100. The code that generates this is very simple again. The only difference from the previous one, besides the model, of course, is that you pass the identical parameters. So Coluna knows that is identical and will solve only once instead of solving 100 times. Now you may wonder, how would you get the solution if what you define in your model is not exactly what Coluna is solving inside? So we provide this active indices function that will go through your axis. In this case, the axis is patterns, because I'm defining cutting patterns, and will iterate only on the indices that you actually used after the solution process. And then you can have your solution. For the CVRP problem, now we have, so the CVRP problem, basically you have a set of trucks, a set of clients. Each truck has a capacity, each client has a demand, and you have to cover, again, all clients. And this says that you have to cover all clients, and subject to your route is feasible, whatever it means for your specific case. And I'm not even bothering putting the constraints here, because in the CVRP, typically you will not solve your subproblem using a MIP. You'll solve something using some sort of resource constraint and shortest path, and some dynamic program. So the reformulation looks like this. It's very similar to the other ones. And I'm telling you this because when you define your problem for a case where you're not solving your subproblem using a MIP, you have your own oracle that solves the subproblem. You don't even bother writing the constraints for your subproblem. You just say, okay, I write my variables. I say what are my master variables, because this we have to define, and then I add this pricing callback. So I take over the solution of the pricing problem, and typically you pass a function, and if you're solving using RCSP solver, you will typically build a network to pass the solver. So this, how would you build a network? For each subproblem, you just take the information on that subproblem and the information on your graph, and then build the network. And for the pricing callback, basically, when it is handed to you, the control, you just solve your subproblem and check what are those negative reduced cost variables, and then you add it to the master. Okay, Now, the last example is where you can go a bit further and do a decomposition inside a problem that is already decomposed. So the example for that is the 2D cutting stock problem. And this problem, it's very similar to the 1D cutting stock problem, except that you're allowed to do 2D cutting patterns to satisfy the demands. So now your items have a width and a height, and you must define these strips. And for each strip, you define a, let's say, 1D cutting pattern. So the formulation looks like this. You must cover all the items subject to the constraints on your strip. This is the stock material and you're cutting it, right? Okay. So the first level reformulation, so this is the original problem and this is the first reformulation. This looks something very familiar with the cutting stock 1D, except that to generate these lambda variables, you have to generate a strip, not only a cutting pattern, not only a 1D cutting pattern. And this is your subproblem formulation. So this is basically to generate a strip. What is a strip? Is a bunch of 1D cutting patterns with the items. And you can say, oh, this looks something like the 1D cutting stock problem, so I can decompose it again. So now you have your original formulation, and which is decomposed, and to solve your subproblem, you solve it through column generation again. So you do a nested decomposition, and this is the pricing reformulation. So the kind of structure that we want to reproduce now is something like this. So we have your big problem here, your master constraints, and your subproblems for your original formulation. And each of these subproblems have its own master and its own subproblems. And the decomposition tree that we generate looks like this. We have your regional problem and your 3 decomposed pricing problems here. Now, the code, so we ignored this part because this is just the formulation for your original formulation. What's interesting here is that now you define 2 axes. And one axis, one of them depends on the other. So the first one, you define a sheet axis, which are your 2D things here that you're going to generate. And then you say how many of them you have, and then you say that for each one of them, you define the cutting patterns, which are the second level decomposition. And then you index your variables and constraints in this axis, and you call the Danzig-Wolff decomposition 2 times in a nested way. And this was it about my talk. Thank you for attention.
Questions?
Sorry?
Do you implement dual stabilization?
We are in the process of implementing that.
So I had a question about the implementation, or kind of how the axis macro works. So it creates some type of object, and then use that later on when you're writing like summations and constraints and things like that. So how does that work?
So briefly, how this works? We use the sparse and dense arrays of JuMP to store which, so it doesn't work with the sparse, so that's something that I'll talk to you guys about later. But for the dense, basically in the JuMP dense arrays, you store the name of the indices and the values and then the variables. So you have a big table and the name of the indices, the axis, sorry, the value of the indices and the variables. And we say that for these, for each of these indices, let's say the machines, I decompose in the I index. I say that this is an axis that we define the axis, block decomposition axis, and we know that they should be split in the subproblems. I know that answer.
I think I'm just looking at the code.
Okay.
Awesome. Thank you.